Thanks so much, DJ. Very happy to be here, and thanks all for having me. Um, let's get to it. So just a little background. I do mostly physics of ocean waves, theory, measurements, numerical modeling. I started off in college as a meteorologist, then I became an oceanographer in grad school, and I kind of ended up doing both, but in between, so basically air-sea interface, and really how to best specify the boundary conditions between the two systems when you have ocean waves. And it's different when you just assume a flat surface, both mathematically and physically. So some of you may know me also from the Fortran world. I wrote a popular Fortran beginners book. Basically, it's a textbook about programming, and that kind of led me into machine learning, part curiosity, part as part of writing the book. I started writing about implementing some neural nets just for my own learning, which is kind of what got me here. And currently, I'm very fascinated with this really explosive development of new methods that was unlocked with certain deep learning architectures in mid-2010s. But I myself, even though I did a lot of tooling, I'm not an ML practitioner. So I don't actually apply it for my own science. And this may be kind of the first time I'm doing it, and everything that you're going to see is very recent, very preliminary. And that's kind of how I like it. I noticed that I like to show kind of very fresh and sometimes dirty stuff in conferences because that's how I get the best feedback early, rather than presenting something that's finished and packaged and then even if I get feedback, there's often not much I can do about it. So first, I just want to give you a little background on my normal work. This is our wind wave tank at the Rosenstiel School. Basically, I would typically run some wind and wave conditions. We put some sensors. On top here, specifically, we're measuring at very high frequency the vertical fluxes, which is what in part specifies the boundary conditions for atmospheric circulation models and ocean circulation models. And from this, basically, we extract derived parameters. Here, specifically, this is an aerodynamic drag coefficient as a function of wind speed, which for a long time was believed to just kind of go up as you increase the wind. Go, Peter.
How hard is it to separate wall effects from your data in that tank?
So yeah, that's a tank size thing. I'm just going to play it while we talk. So this specific tank is 6 meters across. It's 23 meters long. It's 2 meters high. So we have a little bit less than a meter of water here and a little bit more than a meter in the tank. The biggest effect is, if you think back on the channel flow case in boundary layer theory, really what basically the sealing affects the structure of the boundary layer. So we do need to take a few extra steps to make it comparable to the open ocean. Okay, so in the open ocean, a constant stress layer is mostly satisfied. Here it's not. Here stress decreases with height. At the ceiling, it needs to be of the opposite sign, and it reaches zero somewhere in the middle. So that's for a dry channel. But when you have water and when you have waves, things are more complicated. But yeah, basically, we measure things as close to the water surface as possible, and then we extrapolate the rest. OK, so aerodynamic drag coefficient is function of wind speed, which was for a long time believed to just increase. Only 20 years ago, there was first discovery that maybe it does this. It flattens out. So in 2020, through these experiments, we provided a lot more redundant measurements from basically different measurement approaches to kind of all converge to the same behavior, which gave confidence. And this I learned just personal communication in another conference from ECMWF developers, that this paper was what finally convinced them to change the drag coefficient in IFS, and that also fixed their strongest TC maximum winds, which were systematically underestimated. So that happened in about 2021. Now that is not in ERA5 because ERA5 was produced using a normal. So this doesn't fix that part, like when you're training all the foundation models on ERA5, that's not there, but that is going to be there in ERA6. And yeah, so yeah, I just want to point out that like these all the way at the bottom measurements in physics, the effects percolate all the way down to the global AI emulators and what they produce. Another effect that's just from a few months ago done by my postdoc is an effect that won't even be in ERA6. So perhaps in ERA7, because ERA6 is being produced right now. And this is basically, it's not really a discovery. It was a known thing that your conductive heat flux is proportional to the surface area. That's why heat sinks on CPUs or radiators have, a lot of surface area on them compared to the volume, because they want to maximize the flux. So when you have waves, and you have preferentially waves in different regions of the world, mostly in the Southern Ocean, and when you have mid-latitude cyclones, also hurricanes, they all make big waves. So when you have waves, the surface is more wrinkled. So the effective surface area of the global ocean increases when you have waves versus when you don't. And of course, it doesn't increase equally everywhere. So we quantified the correction to the sensible and latent heat fluxes needed if you're accounting for waves. Currently, they're not accounted for anywhere. No climate model or reanalysis data set has this. And it's about globally, on average, it's a 2% effect, or a few watts per meter square. But this it inspired me to show you this, because this also, heat fluxes affect your state variables, but that also goes into your training data set. And Tapio mentioned yesterday that for budgets, even few watts per meter square matter. Now, without this effect, some other parts of the model are calibrated to give you desired SST. So there's a cancellation of errors effect. But if we want to advance, in the physics fidelity of every part of the model, we kind of need to disentangle the processes from one another. Okay, so I mentioned my book, and I do want to use this opportunity to also advertise it. It's very highly rated and popular, but more importantly for this, while I was writing chapter 6 of this book, which was a chapter about derived types, so think structs in C or classes in Python. And at the same time, I was reading a lot of Michael Nielsen's work. He's a mathematician that does a lot of philosophical writing nowadays that is very interesting. So he also had an ebook on deep learning where he implements a neural net from scratch. So I kind of, I emulated that, and I wanted to learn it from my own curiosity how this thing works. So I used the writing of the book as an opportunity to learn about neural nets. Now, what happened was that my chapter draft ended up being 80 pages long, and my editor said, so to teach Fortran, you chose to also teach deep learning, and now you create a monster. So we scrapped the chapter. And I had to rewrite it completely, but I had this code that I made, so I put it on GitHub. And an interesting thing happened. Now, this like kind of summarizes the current state of it. But back then in 2018, when I first put it on GitHub, like I started getting emails, first 1 or 2 a week, then 5 or 6 a week. And they were mostly from China or India. But all emails were, hey, I found your neural net framework. That's really cool. Can you add this feature? Can you add that feature? And people were using it for all kinds of different things, unrelated to my field at all. Yeah, but what I discovered in the process, like it was also, I was invited to write a paper about it. People started contributing to it, kind of the usual open source organic growth. If something catches interest, people will start using it if they have a need for it. I want to say something about this, but yeah, anyhow, it has had some modest financial support too for development, but the key point is it's very nice to use. It has a very Keras-like interface for constructing your networks. You can do dense, convolutional, now even transformer networks. Although the transformer stuff, the building blocks are there, it's just not as packaged as well as I'd like it, but that's just a matter of contributors. All right, but in this talk, going even weirder than that, and I mean weirder, like away from my kind of traditional physics for RC interaction training. So we'll talk about large language models, AI agents. I'll explain what it is, and do they fit and where do they fit in the forecasting pipeline? And I'll try to apply it to hurricane forecasting. Okay. So what you're about to see is definitely dumb. What I mean by dumb is it's a simple thing that I did. You would think that it should not work, but it seems like it could work, okay? Hopefully it's interesting. It was interesting for me, and I think it's going to be useful. Okay, so motivation is there's all these tasks that are downstream from the model output, and Noah showed a much nicer version of this, and just picture that there are little down arrows. Going from model output, you need to do some post-processing. There's a lot of visualization for all kinds of use cases, sometimes even textual reports. And typically, visualization and textual reports go to end users. End users that are typically earth scientists, so more power users. They would also work with the model output, but really most end users work with either the graphs or textual forecasts. Okay, now hurricane forecasting at the National Hurricane Center, which is NOAA's agency that is tasked with operational prediction of hurricanes. Basically, when there's an ongoing active storm, they have a very tight window between each synoptic cycle, which is every 6 hours, to basically get all the data that they have. So that's satellite data, radar data, if there's a reconnaissance aircraft, that the aircraft is sending data back to them. They run some track models based on existing NWP models that other agencies run. And then they prepare forecast. So that happens basically within 3 hours. And then at hour 6, new cycle begins, and it just goes like that until there are no active storms. This is an example graphical product that probably all of you have seen. And if you live anywhere near where there are hurricane impacts, you watch these things very often during the hurricane season. And basically, this is the cone of, I don't know how it's called nowadays, maybe the cone of uncertainty. Tropical cyclone, basically you have, they give you a track, they give you a width of the cone, and the cone has I forget now what exactly is the meaning, but is maybe the probability of, or
it's a climatological error. It's based on 2/3 of the time at that lead time, the track is going to fall within that cone. So it's not dynamic from case to case. It's based on climatological error over the last 5 years.
Okay, excellent. Maria?
And importantly, it's on top of that, the center of the storm.
Yeah.
Right, it's not the
So-
radius. It's not the radius of the storm.
Exactly, just the center, so the impacts extend.
Yes, excellent point. Yeah, see, I'm still catching up with these details. And there's some additional intensity-related and movement-related information here. And there are also text reports. Now, I read some text reports during active storms. I don't know who are the main users of these things, but essentially this is an example discussion that is issued either every synoptic time, or sometimes they do intermediate when the situation is really tricky. They do every 3 hours. So they're intermediate discussion. But essentially this is a text basically describing what's going on with the storm, what's going on with the environment, if some data is suggesting something. Basically, it's a meteorologist expertise and intuition enforced by or constrained by the current available data and models. And basically, they give a summary in a human language about what the outlook is. Key messages, they're pretty short. They follow a consistent format. And they end with a table of forecast positions and max winds. So from current time to 120 hours, so 5 days. Okay. So my hypothesis, and I think many people have phrased this maybe in a different way, but for different things, is that physics are compressed in a database of human forecaster discussions and advisories. So if you read through these discussions, there is meteorological information. There is information about physics and the relationships of how these, let's say, these emergent patterns like a hurricane. So when we describe the flow, let's say we use a system of PDEs, there's no hurricane in there. So if your system of equations is describing accurately the real flow, there is no hurricane. It doesn't exist. But it does exist because we humans need these patterns, like repeating patterns and kind of making an object out of a pattern and then giving it properties is very useful to communicate things. To give an example of this compression, if I say a word hurricane, probably all of you that has some meaning about it. There is, so that's how it's an organized pattern in the atmosphere. It swirls. It also translates. So already there, as you're describing that in language, there are physics very heavily compressed in there. And the compression is lossy. You can't back out the equations from that, but you can extract. There are some higher level abstract relationships that are compressed there. And then you can take down that to deeper level. Is the hurricane moving over a warmer ocean or over a cooler ocean? Is it stalled? What's the environment like? What the data tells you? All these things. Basically, we have because I'm neither a mathematician nor a philosopher, I don't have a language to describe these things. But basically, everything we work with is really language that we use to describe. Basically, it's map versus territory. The territory being the real world, but we only have language to describe it. That language could be math. That language could be just numerical data, and that language could be English or other language. So before LLMs, this kind of meteorologist expertise and intuition on which basically where they discuss the current situation and give an outlook what may happen is untapped in any kind of systematic or quantitative way. And I believe it's possible that large language models can help go from that kind of abstract human level intuition that is stored as text to something quantitatively useful. Okay, so this started with a very small seed grant from my second affiliation, the Data Science Institute at where when this stuff was exploding, they were like, okay, we want to fund small feasibility studies. Just give us any ideas on like how you could use LLMs or generative AI in your field. So I thought of this database of forecaster discussions and see if anything can be pulled out of it. So initially what I proposed was, like at that time, multimodal LLMs, so LLMs with a vision embeddings in them, so you can pass both text and images to it, were emerging. So I proposed that kind of thing where we would take an existing pre-trained vision LLM and fine-tune it on databases of this stuff to try to extract some added value information from new imagery that comes up. Let's say there's an active storm. You feed it radar or satellite images. You could feed it model output. After all, model output is just images. And maybe it can tell you something useful. So this is kind of, I feel uncomfortable constantly about this because it feels like I'm taking a tool and trying to find a problem for the tool, which is usually the opposite to how we work. But, and this is, I'm just giving you a preview. This is kind of the current approach. And I'm not yet, some of these pieces are not there yet. I'm currently still working only on text. But essentially, we're introducing multiple LLMs in a so-called agentic loop. I'll explain what agentic means. To basically have a multi-step process, load whatever data is available into the context and inference time. So we're kind of moving away from fine-tuning a foundation model to hopefully get you either an estimate of the current state of whatever the key parameters, or perhaps even a short-term prediction.
Sorry, did you say what LLM you're using, or is that next?
Yeah. Okay. So I think by now everybody's using LLMs to some extent. So I'm just going to go very briefly on what they do. So basically, they're unsupervised, in an unsupervised way, trained on large amounts of text. So basically, on the whole internet. Think Wikipedia, open books, Reddit, things like that. And they auto-regressively predict the next word. Now, that's a simplification. They don't even predict the word. They predict the token, which is part of a word. But just for illustration, in each inference step, they predict the next word. And they just kind of go on. And at your end, you end up with something hopefully coherent. And this here is a really great book. It teaches you how to build an LLM from scratch, and I recommend it. Like inside, so I already mentioned that the text is broken up into tokens. So these tokens are then converted into floating point value counterparts. And these floating point values are then piped into the transformer, which is a neural net architecture. But you can just think of it as a giant matrix multiplication. and you end up with floating point numbers at the end that is then converted back into text. And here with this diagram, I don't need to use a lot of his details here. So these are all from this book. But I want to point out that basically large LLMs are pre-trained in an unsupervised way on a lot of text. But what you're using as an end user is not a pre-trained. Foundation models, there's always some fine-tuning step going on to either align the model to your use. So is the model meant to chat? Is it meant to produce some structured output? Is it meant to classify or identify things? And that's done through fine-tuning, typically supervised. There's also the reinforcement learning part, so-called human in the loop, that I won't go into, and I don't really understand it, to be honest, but it's not relevant for this talk. I want to give you a few example responses from small LLMs. So I started with small LLMs because I wanted to work with something that I can push to its lower boundary of capability, something that I could run locally quickly, and something that is at least open weight. Now, so what you see here are outputs from 3 different models. They're all Llama models, but the latter 2 are 3.2. They're smaller models, and they were released later. This is a little bit bigger, but this is still much smaller than, let's say, what you're getting now from GPT-5, about 100 times smaller. But this can run on a commodity laptop with a tool called Ollama. There are other tools, but Ollama is really easy to get. And you just tell it what model you want to run. It's going to run it on your GPU if you have it. If you don't have it, it's going to run on CPUs. It's a very turnkey, easy solution. And I ask it a simple question. Where and when did Hurricane Dorian 2019 rapidly intensify? So I don't want to ask it something so obvious and easy. And I also don't want to ask it something too deep. But I kind of played around with it to giving it an example that a little bit bigger models can succeed at and smaller models can fail at. And that's what we see here, going from 8 billion parameters to 3 billion parameters to 1 billion parameters. So the first one answered correctly. The second one answered incorrectly, but concisely, but also it didn't make up other stuff. This last model is all just garbage. No.
Are you prompting it with the forecast reports here, or is this just like asking the model?
No, this is just me toying around, giving it one question. So there's no prior. So there's only, the only information they had is in the weights, pre-trained. Okay. And even with open weight models, I actually don't yet fully know what goes in it and what doesn't. For example, every important hurricane gets a Wikipedia page, and all of this stuff is trained on Wikipedia, so they will know about these historical storms. But really, if the model is too small, like it can only get so specific with the information. So it kind of becomes, like my experience is like, it's almost like the smaller model you get, it looks like they had more and more drinks the night before.
Sorry, I have a question. Just a clarifying question about the 3 models.
Mm-hmm.
I know that they are different in terms of their parameter size, parameter numbers. But what about the size for their training data? Are they exactly the same? Do you know?
I will need to get back to, I don't know. So there is an important relationship between model size and the size of the data that you need to make an impact on the model. I will mention that. That's more important that's a bigger constraint for pre-training versus fine-tuning, which I will talk more. now. Okay, so this was my first attempt, taking an open weight pre-trained, wrong button, pre-trained LLM, fine-tuning it with the NHC archive. So I'll tell you more about the archive, and then hopefully giving it an example input and then getting something better than what I could do with just pre-trained. Okay, so the archive is, okay, now it's about 20 years long. Here I'm still using the data set I compiled for 2006 to 2024. 674 storms, about close to 60,000 text documents. There are 4 different types. So for fine-tuning, I used it all. Later on, I will explain why I'll use only discussions. And this is a very small data set in the end. It's 185 megabyte size, only 55 million tokens. So there are some rules of thumb that people have established in the literature of how many tokens do you need in the training data to successfully pre-train an LLM. And you need at least 20. So to pre-train a model with this, like I would have to work with basically a 2 million parameter model. But we saw in the previous slide that even a 1 billion parameter, when trained on a bigger data set, is incoherent. So, I mean, that just rules out any kind of pre-training. Now, this could be added to basically to the internet database during pre-training, so that would fix that. But then you're limiting the detail that you can get. So really, the way to go is fine-tuning. And size matters much less for fine-tuning because I'll explain here. So in fine-tuning, you're really only changing the weights of a small fraction of your model. So I took Llama 3.2 with 1.2 billion parameters, but less than 1% in my fine-tuning setup is trainable. I believe it's only the last layer. And I'm using this method, which is quite popular. It's quantized low-rank adapter training. It's really just a way of calculating basically an adapter matrix to the weight. So you're not changing the weights. You're essentially only calculating these A times B smaller matrices, and then you're adding them in the post-processing step to the pre-trained model. Original weights are left untouched. Now, we have an HPC system at with large memory GPUs, but the support and software ecosystem just didn't allow me to set up. I mean, all of this stuff is kind of from, like the code, the libraries that you pull in is all from last year or two. And I just couldn't set it up on an IBM Power 9 system that had things pre-built from 6 years ago. So I just kind of worked with my laptop GPU, which is a very small RTX 4050, 6 gigabytes of RAM, which limits first of all, it limits the size of the model I can pre-train, I can fine-tune, and it limits the the context length. And fine-tuning took me about 30 hours to run, and these are some training metrics, evaluation loss. So we start from about 2.6 and very quickly drop to here, Peter?
What was the task? Like, what was the fine-tuning task? How did you tell it what to optimize?
Summarization. So that's also a thing that I'm still kind of exploring, like what's best for this. So this is kind of what I started with.
So summarization means this array of numbers that you showed us earlier about wind speed and so on.
So if you gave it, basically if you gave it text, it would correctly extract the information in it. Now, my goal was also to for it to pick up specific information about hurricanes in the training data set. So maybe summarization was not the optimal task. And it may be in part why my fine-tuning failed, which I'm going to show you on the next slide. So like one thing to note is that this very quickly converged. Like in less than half an epoch, most of the convergence that would happen was there. So one epoch is essentially the size of my data set that the model has seen. And basically, I stopped after 2 epochs. And I just ran it on many tests. I'm showing you only one. Basically, I'm giving it. Now, this is not a summarization task. And maybe that's part of the issue. But essentially, what I have created is I made it learn the vernacular of NHC without picking up the specific information. I think that's becomes more of a data pre-processing problem, because then if you analyze the text, so much more is really in these kind of common words that are used to describe things. But the actual specific values that I'm going after was simply not picked up. So I did not notice a gain in specific knowledge, but I also noticed loss of general coherence. So by adding something to the same size model, you have to lose something from it. So usually when you add specificity, you lose generality a little bit. I believe that's what I'm observing. And this I just said. Another thing that I lost here, and this may be simply my newness to this field, is that I started with a model that had tool calling capability, which will be important for agentic stuff, and I managed to also destroy the tool calling capability.
So a question from so by coherence here, do we mean that at some point it might stop even producing like valid English, like complete gibberish? Can that happen as well?
So it gives valid and probably to a non-meteorologist reasonable English, but me knowing what's in the training data and how these things work, yeah, basically it goes off to ramble, essentially. So whereas the foundation model, it was more capable of giving concise and to-the-point responses, it seems like somehow I had destroyed also the capability for it to just stop.
Yeah, how does it stop actually? When does it know when to stop? Or
I don't know.
It predicts a stop token. Yes. So that's one that's like stop.
Yeah.
So I may be misunderstanding the intended purpose, but you're fine-tuning it on these NHC discussions, right? Which are themselves already the lossily compressed data from the model output. So
Yeah.
if you wanted to not lose all of that information that's lost, wouldn't you want to fine-tune it on the various model outputs and the satellite images and et cetera, and then maybe direct it to produce an output similar to the NHC discussion?
Yeah, possibly. I mean, yeah, initially I proposed fine-tuning with images too. What happened over the year is that fine-tuning was mostly by the community, by the LLM community, obsoleted by agentic bringing in data available into context, because the context size has grown so much that now you can load a lot of stuff right there at inference time. Okay, so this is now very recent, and that's a change of paradigm. So essentially now LLM is wrapped, to access different LLMs, but from a same clean code. You usually use an API that unifies that. There's a lot of libraries that provide you, kind of from a language point of view, nice access to API. And then to orchestrate multiple steps of LLM inference under the hood. You use an agent framework. There are several popular ones now. I'm using Pydantic AI. And then around that is my code that is basically telling this agent framework what to do. And what do I mean deterministic AI agent? Like in retrospect, I realized deterministic was not a fortunate choice of the word. But deterministic, I really mean that because by default, LLMs just output unpredictable length and structure. Here we require consistent structured output following a specification. And by AI agent, we simply mean a multi-step pipeline of LLM inference. And the recent developments have been not only that it can, that it can feed to itself. So you've probably noticed when you chat with AI that it will do the thinking. Sometimes it will go search the web. So that's also, we call it running tools. So it can run the code on a local computer, load the data locally, and basically put that into context and inference time. And you can also make it, so this is more programmatic from an agent framework level. You can make it adhere to a requested format like JSON, which is important if you want the output of this to feed into the next step in some automated system. Okay, so we're getting to the dumb part. I'm going to try to simulate real-time ops by only providing prior data. So we have these discussion products. This box just symbolizes a file, a chunk of text, which is an NHC discussion at T0. And I give this to an LLM that reads available data. So when I step further in this, when I go further along in the storm's history, I also give it the full history of that storm. Basically, not only the previous discussion, but I give it all previous discussions. So to give it the full history of the storm as we march forward. So then I ask it to pretend to be an NHC forecaster and predict the discussion 6 hours from now. So basically, it has to imagine what the storm will be doing and what that will be looking in meteorological terms. And then I have another LLM that takes that and extracts this into a structured JSON. So yeah, I cannot summarize this. I have a forecaster and an extractor. Now, I test 3 models, and unfortunately, here, for the sake of time, I had to go with closed models. Because what I found when I work with much smaller open weight models that I could run, they're pretty poor. They had poor performance with tools. So essentially, they would fail at the task most of the time. Running the GPT-5 family allowed me to essentially run these things quickly and in parallel because they're just API calls. The things are computed over there on their servers, and they return the response. Now, in terms of parameter size, Nano, which is a very small model, is estimated to be, so this is not open information, this is not documented, but people have done studies and kind of reverse engineered, based on performance, what could be the size of each of these models. So we're talking about 10 billion, 100 billion, and 1 trillion parameters. So 10 billion parameters, which is the smallest one here, is already 10 times larger than the one I was trying to fine-tune. OK, and then you need to give it very specific but concise instructions to not kind of let it go do whatever it wants to do. So you give it specific guidelines that you know, let's say as an expert meteorologist, and I don't know if I would call myself an expert meteorologist in terms of like the forecasting of hurricanes. Like I work a lot with like physical processes that matter, but I won't make a good hurricane forecaster. So somebody could definitely help me make a much better system prompt that would steer the LLM to use available information correctly. And then this is the example NHC text pro that I showed you earlier, but I want to point out that this table, so every discussion has a table of predictions. I stripped that from the input to not give an LLM idea that it should just forecast whatever NHC forecasted already. So it will take the meteorological discussion. I'm not giving it numerical values, but I'm asking it to produce numerical values. And here I'm just showing you a snippet of this Pydantic AI code where basically you give it an output type as a class, which specifies like the structure that the output must have if the model is to succeed. But in addition, I found that you also need to explain things like what the data should be. And if you do that, it is much more capable at fitting stuff into the specified structure. Otherwise, it can just fail. OK, so this is my first test case. And I want to point out that this is Hurricane Dorian, which was a very high-profile storm. It's also a historic storm, meaning that it is in the training data of the models I'm using. And now each of these lines, so this here with color markers is the actual track that realized. The blue, green, and orange lines are individual track predictions by LLM. Now, I want to remind you that each prediction is made for 6 hours, from 6 hours in the future. So there is no textual data at that time. I'm kind of enforcing that to simulate a real-time operation. Basically, I don't want to give it basically from that time future data, so then it just knows what to do. It knows where the hurricane will go, but because this is from the time that is in the training data set of the foundation models, it's more of a test of like, OK, does this produce something reasonable or not? This is what it looks like for the intensity. So all the cases I'm going to show you were also rapid intensifying cases. And in general, these, like NHC does often too, but also the LLMs don't quite capture the rapid intensification. But the general trend, like if you squint your eyes enough, you will see that these color lines do kind of go in reasonable directions, both while the storm is intensifying and while the storm is going down. You may also notice that in general, overall, the orange will be doing better than the green and the blue, which is really the test that I wanted. If I increase the model size, we'll be able to create something more useful given data. Adam?
Can you say about like what tools they have available? Like, is this just really a tool use task since this is a historical storm? Is this information available for them to look up with a tool?
So when I'm calling LLMs through the API, there's no agentic flow there on that end. They do that because they want your cost to be predictable. So you only get one inference step without tool calling. You can enable tool calling explicitly, but everything that returns is without web search. So it's only what's in the weights. But it's important to remember that for all GPTs, Dorian will be in the weights because it was in the training data. I'm pretty sure they're not training on NHC discussions, but they're training on Wikipedia.
But this information wouldn't be on, this level of information wouldn't be on the Wikipedia, would it?
No. So that's the crux here. That information it's getting from the text of the prior discussions that I'm giving it to. And for example, these guys here that are starting from the peak, they're starting from there because they're getting discussions from all the way from here and here. Thank you. All right. So these are the errors for Dorian, but I'm just going to skip this. You know what? I just want to point out. So black is the error of the actual NHC forecasts. And given only prior NHC discussions to the LLMs, they're getting pretty close. The errors for track are bigger. But what I was looking for is that as I increase the model size, this should get closer to the black. And again, this is a dirty case because it's in the pre-trained. It's in the weights. So we need something that's outside of the weights. GPT-5 was released in August, and this storm happened in September. So we know that this storm is outside of the training data. So the models never saw the storm. But they're getting the NHC discussions that I give it up to the time. And yeah, they're taking things in a generally nice way. Really, what I was looking for is that I was hoping to not get Brownian motion. So the fact that they're going in a certain reasonable direction is a positive. This is what it looks like for intensity. And then Michael yesterday inspired me to do also Melissa, which was another high-impact storm in October. And here, actually, the discussions didn't start until about here. And it had a pretty complicated track in the Caribbean Sea, and it even slowed down and stalled at some point, rapidly intensified, and then went across Jamaica and Cuba. So a lot of these, I mean, it may seem impressive that it's taking things, close to the track, but it is getting hints from NHC expert opinion from the prior discussions. And another thing that I was looking for is the later I go in forecast, the more input I give it, the forecasts do improve as we go further. This is the same thing with intensity, and actually, I didn't quantify this, but I can almost eyeball that there was some rapid intensification in the LLM predictions. And since I'm out of time, these are my takeaways. Basically, this is a very preliminary prototype that I think has potential to be improved by bringing in especially imagery in the real time to basically really give it a lot more context and inference time. And I want to thank you with this excerpt from Forecaster GPT-5. This was for Melissa approaching Jamaica landfall. Thank you.